All right, well, we'll start back here. This is the last chapter of Unit 1, getting into soils. I guess before we get started, I did want to just put a little bit more detail behind something on what we were talking about last week with the climate, and I think I just didn't drive it home enough, the whole thing about growing seasons and hardiness zones. So we look at our growing season based usually on annual crops is what we're thinking of there. So warm season annual crops is what we think of as that regular growing season governed by the frost-free period. And I said that for the hardiness zone, it really only applies to, what perennial crops you might grow. And so for perennial crops, I mean, it's not like a huge thing in terms of field crops. All of our field crops are pretty much annuals. Our corn, soy, wheat. But I think a lot of you all that are into kind of more animal production, perennials do play a huge part in that, and pasture grasses, things like that. So we have to look at what grasses are hardy for our zone, or tree fruits, plants like that. So our hardiness zone here, being a 6B and going to that, supposedly -5 degrees of hardiness, can, so-and-so variety of this tree or this particular variety of pasture grass, can it handle that hardiness? And if we think about like the plants that are kind of native to the ecotype and native to our region, those generally are going to be hardy and well suited. And so some people actually look at managing native, like warm season grasses as part of their pasture management. But a lot of the things that we put in for crop production are not really the native organisms. We're bringing them from somewhere else. So you think about, is it hardy in that place? And in some ways it does apply a little bit to crop production, because it is, based on temperature, our, lowest low, and that does sort of play into the growing season, and maybe to a degree when frost arrives or when frost ends. But mostly that hardiness zone is just looking at how freeze proof is it. And there are ways to modify that, looking at the microclimate by, say, fig trees, for instance. They're not very well known for being a good fruiting crop in zone 6 or 7. But if you get the right microclimate, a little area that's maybe a little bit warmer, it holds a little bit more temperature, a little bit more warmth longer in the season, then sometimes they can produce fruit, even though we really say that they are hardy to, like, depending on the variety, some of them are hardy to zone 6. We might not have a long enough growing season to actually get mature fruit. So you have to look at both the hardiness, as will the plant even survive, as well as what are those frost-free dates, what is the length of that growing season, and will that crop mature in that number of days. So I'm actually just getting ready to dig my sweet potatoes, and that's another crop for us that's, you have to be really careful about your selecting the right variety, because it has to fit in that window of days. And what I'm waiting for right now, and it could come any day, we usually say that October 10th is our first frost date, but it's been as early as late September in some cases, and as late November in some years. So it just depends on the year, what the weather is like, not always looking at the climate there. So what I'm waiting for right now is these sweet potatoes to actually go to seed. That's kind of unusual for sweet potatoes in our area, but this particular variety, Stokes purple sweet potato, which is an heirloom from the mountains of North Carolina, it does flower and actually produce seed. And to me, that's a good trait, because if it produces seed, you can start some plants from seed other than just doing the traditional starting it from slips, which means that you have to be able to maintain, slip production, save enough sweet potatoes back to get them to produce slips. If you have seeds, then you can start them earlier indoors. Also, they have a little bit more of a chance to, kind of hybridize and get some new traits. So anyway, that's what I'm waiting for right now. And it's funny to look, because I've got sweet potatoes that are ready to be dug out of the ground. A lot of sweet potato growers would say, yeah, you don't ever want to get any frost on that. You want to get them out of the ground before that. But because I'm looking at seed production, it's a longer growing season. So it's not even just the crop itself, it's what are you trying to get from the crop. The sweet potato itself is ready to dig out of the ground, but the seed production is, tuber production, we're looking at like 120 days. Seed production is probably more like 150 days. So can I leave it in for another month and not have frosts? So that's a kind of long-winded explanation there, but I guess what I'm just trying to drive home is that we have to look both at that hardiness zone as well as the growing degree days, the frost-free period, and of course, your microclimate. So where are you growing it, and how does that kind of microclimate modulate the effect of temperature and wind on your crop? Any questions there? All right, well, let's talk about soil. And get my screen up here. All right, does that pop up for you?
There it is.
So we're talking about soil. I think it's one of the most important things that we can manage properly in order to get, good crop production for anything. I mean, it all starts with the soil, and soil is alive, really. It's got life in it, and that soil determines, really, to a great extent, how productive our crops can be and how we manage the soil. So soil is basically broken down rock. And we consider that broken down rock parent material. So this parent is a big deal, and we think of that as being either the sedimentary, metamorphic, or igneous rock that basically determines what the soil can become as it breaks down through weathering over centuries, really. So it starts with parent material, but then we look at the climate, the topography, the lay of the land, as well as the organisms, both in the soil, on top of the soil, the plants. All of these factors kind of integrated and interacting over a long scale of time determines, what our soil is like. So in the image here, you can see that it's kind of a sloping. You can actually see looks like some erosion in here, where it has that kind of steeper topography. So how topography plays a role in it is that it's moving that soil, and as it moves, it either gives it a chance to decompose more and become soil, or less, depending on where it's moving, how it's moving, where it ends up staying. So at the bottom of this slope, the soil is going to be much deeper, whereas at the top of the slope, it's going to be more shallow because it's moving from there, moving down. So the climate, of course, affects the rate of weathering. So we look at warmer and more moist climates as breaking down the rock quicker. And Also age, so over time we're going to have deeper soils, depending on what type of weathering you have going on. The type of plants growing on it are going to affect the soil, as well as the soil affects the type of plants that can grow. So it's very important to look at that and just think about how both plants are living, above ground, and they almost have as much mass below ground. So soil is important to look at in any kind of plant production, whether it's even in like a hydroponic kind of controlled environment agriculture setup. You still have these kind of principles of soil, something to anchor the plant into the ground and provide it as a root zone. So as I mentioned, soils are composed of this weathered rock, which is the parent material. But it's also got air, water, and decomposed organic matter, which is just things that came from living things, as well as currently living organisms too. And it consists of kind of four main parts. We got the solid fraction of the soil, which is the actual rock itself and the minerals associated with it. So that parent material, as well as it breaking down, and sometimes you'll have big chunks of rock, sometimes you won't have any rock. But nonetheless, the soil came from that solid fraction, that rock itself. Then we have a much slimmer organic fraction, which is all of the decayed and dying plant parts, as well as animal parts too. Your bones, manure, whatever returns back to the soil, becomes part of that organic fraction. So that's like half of soil right there, the solid part that is basically rock and organic matter. The other half of soil is a mix of water, and water, as it moves through soil, contains a lot of these dissolved minerals that become plant nutrients. And there's also air in the soil. And so we think of almost like a soil atmosphere. It's very important for there to be a good balance of water and air in the soil. We think of plants, being able to, absorb carbon dioxide and produce oxygen, but they still need oxygen in the roots. They don't produce it and just move it down there. They release that from their leaves. So we have to have oxygen in the soil. Little pockets, the pore spaces in between the solid and organic fractions are where we have water and air. And that water and air, this is also ideally, especially like in an agricultural soil, that's the other half of soil. And we want it ideally to be kind of half and half, air and soil, for a plant to be productive and photosynthesizing well and growing a lot. But of course, that liquid and kind of air fraction is in flux. It's always changing with the amount of rainfall that we have, whether we're irrigating or not, and also our actions and the way that we manage the soil. So say you compact the soil by driving your tractor over it. You're reducing pore space, and you're reducing the ability for air to be in it. So we change that significantly, not just once. We change it often over the growing season. When we plow and till, we're changing that soil structure, so we're changing the liquid and air aspect of it. So the kind of soil and the ability to support plant growth are really influenced by the relative amounts of each of these components. And it does become this very complex and dynamic system of all these interacting factors that are affecting the soil and affecting the plants that grow on the soil. So as I mentioned, the void, the area between the solid portion of soil is the pore spaces. And those are going to vary in size, as well as where they are, depending on how we manage the soil, as well as how that soil forms. And those are the kind of, we looked at in that first slide, the 5 factors of soil formation, or that the parent material itself, your topography, whatever plant and animal life is on it and in it, organisms, and then finally we have just the interaction of these factors together with climate over time. So we look at that solid phase of the soil as usually being like 40 to 45% mineral and up to about 10% organic in volume. And again, that organic portion is also in flux, because the things that are living in the soil are breaking down that organic matter all the time. So, soil can have very little organic matter in it, and I mean, it can be less than 5%. Often it is if you're not adding some sort of organic matter back into it. I think that's one of the most important things in management of soil that people forget to do. We think about just adding fertilizers as a way to have healthier soil, get the nutrients, but really adding organic matter is one of the best things that we can do. So anyway, solid phase, that's half of the soil. Most of it is the mineral that's been broken down from rock, and then there's a slim proportion of the organic matter that is kind of in flux. The other half of it is filled with this mix of air and water, and that's going to depend on the moisture in the soil. Ideally, what we want in an agricultural setting for it to be productive for plant growth is a soil that is about half pore space, so it can drain water quickly, and then half of it actually filled with water, so that, and holding on to water. So we need a mix of large pores, we call the macro pores, and small pores, the micro pores. The macro pores tend to hold air more and drain water quickly. The micro pores hold that water and actually allow it to move in different directions, even up against gravity by capillary action and capillary forces. When we look at water moving through the soil, it contains these dissolved minerals. It's very important for plants to actually get the nutrients they need. We call this kind of field capacity. So think about, either watering or after a big rain event, that water is going to move through that soil. It's going to percolate through it and it's just pulled out by gravity. And once you get to that point where gravity has pulled out all of the water that it can just through gravitational forces, what we have left is field capacity. And that's when we start getting to plant available water. So plants aren't really like drinking the water out of the soil as the rain is falling necessarily. That's, it does help. Plants can actually absorb a little bit of water through the leaves. But it's actually this period of time afterwards, after that water has drained through the soil, it's what's left in those micropores, and that's the field capacity, and that's where we get into water actually being available for plants to drink and grow and use. All right, so looking at the parent material, basically, we talked about this in, earth science probably, even in elementary school, we talked about it at some point, 3 different types of rock, right? We got igneous, sedimentary, and metamorphic rock, and they each have these different properties that affect how that soil ends up, being, and what the mix of the different particles in the soil, that mineral fraction is based entirely on what rock was there in the first place. So, of course, we look at the igneous rocks that are formed from basically volcanic action. You know, it was once magma and then it hardens into stuff like quartz and feldspar. And that igneous rock is very important for particular nutrients and a particular texture of soil. And in Ural's part of the state, we're actually in different, we call physiographic provinces. And the physiography is based mostly on really all of those same soil forming factors, but the big thing is what rock was there. And we here in ours is the Ridge and Valley province. You guys are in the Piedmont. And in the Piedmont, you have more igneous rocks. So you have a totally different soil than we have here in the Ridge and Valley province, because we have sedimentary rocks. And sedimentary rocks are basically, they're kind of like a composite of a lot of different rock types being broken down and then moved and deposited and then cemented together somehow. So the most common examples of sedimentary rocks that we have are limestone, sandstone, and shale. And different soil types develop from different sedimentary rocks. We often see things like fossil imprints in sedimentary rocks as well. But like a limestone breaks down and gives you a more calcium rich soil. Of course, we use limestone, actually kind of mine it in a way and turn it into agricultural lime that we use to raise the pH of the soil. Another important part of the management of the soil. But limestone breaks down, it gives you a fairly sandy component and a little bit better plant nutrition. Sandstone, of course, breaks down into sand. Shale breaks down more into clay. So it's not even just saying that we have sedimentary rocks, but different types of sedimentary rocks here and there, which give rise to different soil types. Metamorphic rocks are those that have been formed. Usually it can be igneous, but it has often been kind of taken underground again and then subjected to really high pressures and temperatures that change the original nature of the rock, changes its structure and composition. So we think of things like slate and gneiss, schist and marble being metamorphic rocks. And those metamorphic rocks, again, break down into different soil types. So slate and schist tend to make more clay soils. Gneiss makes more of like a sandy, silty type soil. So it's not necessarily just due to the rock type, whether it's sedimentary, igneous, metamorphic, but what the actual minerals were. And then that leads to specific plant nutrients. So kind of rock, parent material is kind of the first thing I think of anyway as determining a soil type. But we go back to all of these different processes in both accumulating and then transforming that parent material and turning it into soil over thousands and in some cases really even millions of years. So parent material is accumulates from this breakdown of rocks by weathering, and in this process of that weathering, the interaction of the climate and the topography over time, it develops slowly into these different zones called horizons. And we look at all of these horizons together and kind of how you distinguish the horizons to develop into this soil profile. So soil science, we study soils based on that profile and how it's developed into this kind of cross section of soil extending through all these horizons, all the way down to the parent material, the bedrock, which the soil formed from. So we look at that type of parent material as well as how it weathered. And that's going to depend largely on the climate, as well as the life forms, the organisms interacting with it. So weathering, which is just, of course, the physical breakdown of large chunks of rock into smaller and smaller pieces, and eventually into the microscopic particles. So we have basically just the breakdown, the contraction and expansion of the rock itself just through temperature changes that causes like a cracking or pilling of rocks. That causes this exfoliation. We also have glacial till in some areas, and that's really important in the Midwest because it deposits rock as well as kind of acting like a huge plow in many ways, moving and breaking down that parent material. So again, the Midwest is like the breadbasket of the world, and one of the reasons why it is because it was recently the most recently area that was glaciated, and because of that glaciation, it's deposited so much really deep topsoil, which makes that an extremely productive area. Of course, the climate has, is a big part of it too. It's dry enough to produce good seed crops for feed, like corn and wheat, and it's usually dry in the harvest season, but there's enough water to grow the plants in the growing season. So it's a combination of factors, but really I think it starts with the soil itself. So looking at that parent material and some physical weathering, in this image, we think of like glaciation, but what comes after that, we have just the movement of water. Usually that makes a path for there to be, waterways, eventually rivers. So in this case, we've got a, massive gully here formed through stream erosion and periods of heavy rainfall, probably where the soil was not managed very well and it ended up running off. Either way, you can see this kind of soil profile here on both sides. And in this case, this looks like it was coming from the Midwest there, because it's really deep topsoil, several feet of this kind of dark soil. But that in itself, it's physical weathering. It's moving the soil particles themselves to a place where they can then undergo different types of weathering, such as chemical weathering. And chemical weathering, it's really a combination of, it's due partially to physical weathering, but it happens partially from dissolution, which is where that parts of the parent material rock, some of these minerals will dissolve in water. Even rainwater is naturally acidic. So if you take limestone, for instance, and continually put just rainwater on it, eventually it'll start to leach away some of those nutrients, some of those minerals, and break down. So what we're having with this dissolution is it's kind of dissolving in a way, but it's moving those minerals into the solution, the water, or whatever it is, the acid that's breaking it down and moving those away. So that's chemical weathering. We've got hydration, where it's adding water molecules to form a different chemical compound. Similar to that is hydrolysis, which is just the reaction of the compound in water that then makes a more soluble and more reactive product. And then finally, we've got oxidation, where basically it's interacting with oxygen in air. And we think of oxidation as often making like a orange or kind of red reaction in the soil. because it's basically rust. Iron in the soil reacts to form iron oxide, which is rust, and it gives this kind of orange or reddish color, which is not necessarily a bad thing. You know, generally we think of, oh, that soil's just red clay. It's not, you know, worth a thing, but it still can be good soil. It's not just because it's red doesn't mean it's bad. It just means it's been oxidized. So climate, of course, is one of the big factors in how long it takes for the rock to break down into soil. Of course, it's important for what plants can grow on it, which then affects how that rock breaks down as well. So if we have higher rainfall, then generally we're going to have a more highly weathered soil, basically. It's going to affect both the chemical and physical weathering processes. So it's kind of a mixed bag, really. In areas of really high rainfall, like tropical rainforests, we have soils that are often really highly leached and are usually very, very acidic too. So they're not great at that point. Causes low soil fertility, and a lot of those nutrients, because they're leached from that zone, becomes difficult to grow crops on it. So they say when you like clear rainforests, for instance, to grow crops on it, you can't do it for very long because there's not natural fertility there in the soil. In arid climates, though, in drier places, the soils are not highly leached, and that in turn leads to accumulation of some of these nutrients that are otherwise would be leached out. So calcium and magnesium carbonates are very often found in like desert soils, and they cause chemical weathering to proceed much slower. So these are actually both salts technically, not like sodium salts, but just their chemical compound is in like a salt form. And this accumulation of salts is a big issue in these arid climates. Often these soils can't be productive until those salts are flushed. Usually we look at adding large amounts of fresh water to get that effect. But we see that a lot in very productive areas of soil. It's just how you manage it. So Central Valley of California, I keep referring to, another very important agricultural area in our country, but also around the world. This is a huge problem there because we're moving more salts into the soil. Every time we fertilize, we're basically adding salt to the soil. And sometimes you have to flush those. The way that different life forms, the biology interact with the soil, I mean, it's many different ways. It affects both chemical and physical weathering. First thing that you might think of is just the root mass itself. So up to about 50% of the plant's actual dry matter is there in the root system. And it could be as little or maybe even less than 10% in some cases, but up to about half. So maybe a way to kind of visualize that and think about it is just, you know, think of a tree, look at that tree above ground and think about that same root mass being underground. It's not really, it's not like a perfect ratio like that. And it's not going to be a mirror image either. It's not like, all right, the tree grows 100 feet tall, so the roots are going to be 100 feet deep. But nonetheless, just kind of visualize that and just think that that's about the possible mass of what is underground. So those roots, of course, are there to support and anchor the plant, as well as absorbing water and nutrients. And in some cases, for some of our crops, they are providing food reserves, a form of storage for the plants. Like in my sweet potato example, you know, that's what that plant is doing. It's storing its energy in that root mass. So with different weather, as those roots die, they become organic matter, become part of the soil themselves. And when we look at that root system, we've got generally, a taproot. All plants have a taproot, but think of one kind of long root coming down initially, and then all these little feeder roots and root hairs coming off of that root tip. And those are absorbing the material from the soil, not just the nutrients in the water, but they're also absorbing the carbon and the hydrogen, the oxygen, the components of the organic matter. So that's what's causing this flux, this fluctuation of the organic matter in the soil, is that plants' bodies themselves, if you look at plants' dry matter, it's mostly carbon, hydrogen, and oxygen. And that carbon is coming mostly from carbon dioxide in the air or carbon from the organic matter in the soil. So something that we've done in the past, kind of as an experiment, also just kind of because it was the easiest way around, is we filled raised beds with just compost and just grew plants in straight up compost, which is primarily organic matter. And in doing so, we saw that soil level decrease from the raised beds themselves were 16 inches deep. And by the end of one growing season, they were more like 12 inches deep. So we lose like 4 inches of soil of that organic matter just going into the body of the plant itself. It's kind of neat to watch. You don't really see that as much if you're just using, a regular soil that's, broken down from that natural rock, because it doesn't break down further. It's not absorbing those soil particles, but it is absorbing the actual organic matter, if that makes sense. So also, plant roots can secrete chemicals into the soil that can also help to break down the rock itself. And as I mentioned, the old roots are going to die off, and then they're going to be replaced, so that more than half of that root system will be turned over in one growing season. Pretty neat. All kinds of crazy things going on underground. And one of the things is just the sheer amount of life in the soil. There's actually been a lot of research on this in recent years. There's a whole food web of soil, going on, life cycles underground. And it's interactions from all of the kingdoms of organisms, from the plant kingdom, the animal kingdom, fungi, protists, and bacteria, the minerans. They're all affecting the formation of soil and the growth of plants. So it's interacting as an ecosystem underground as well as above ground too. And it affects the soil's chemistry, its structure, and its functionability. So first, we got bacteria, which are the most abundant soil organism. And they say that there can be up to 1 billion microorganisms in 1 teaspoon of healthy soil. And probably like 90% of those would be bacteria. Mostly unicellular organisms that are both good and bad. Some of them can, actually feed on plants, be parasites. Others are feeding on other organisms in the soil, both good and bad. But a lot of them are just involved in the decomposition and recycling of nutrients in the soil. And this is why I think adding organic matter is extremely important, because when you add organic matter, you're providing food for these microorganisms. Fungi, same deal, extremely important, breaking down that soil organic matter so that the plants can absorb it. We also talked about mycorrhiza and that symbiotic relationship that it has with plant roots, basically to help increase the uptake of nutrients and water. All kinds of other I think of them as intermediate organisms, the protists and algae, that have different things both on the soil surface and underground. Again, good and bad. Sometimes they do good things for us. Sometimes they do bad things and feed on the plant roots themselves. And then, of course, we have lots of animals, ranging from these little worm-like creatures, nematodes, up to snails and slugs and crustaceans like the roly-polies or sow bugs you see in the soil. That's all part of kind of this breakdown of it. And again, for better or for worse, they can feed on plants or they can feed on other things in the soil. They can be good or they can be bad. Either way, we have a very rich soil biology, and it affects how soils are broken down. So we've got all this non-living stuff interacting with this living stuff, and that is determined in part by the climate. So how much rain and how much temperature fluctuation we have is going to affect the life, which then affects all the other factors too. So it's really everything interacting that makes the soil type and determine whether it's productive or not. The amount of just organic matter itself is influenced by, of course, these organisms and the climate. So if we have cooler areas, then it breaks down slower. We have warmer areas, higher moisture, it breaks down quicker. So generally, well, I guess it's not always just affecting how quickly it breaks down, but also it can affect organic matter accumulation. So if the decomposition rates are high, then and we think of that as often being warm and moist, accelerating decomposition and increasing organic matter, and for a period of time, its availability to the plants, but decreasing the soil organic matter in the long run because the plants are absorbing them. But in very wet areas where there's water in the soil, then it becomes anaerobic. And anaerobic is just meaning without oxygen. So that inhibits the decomposition, allows that organic matter to accumulate. So we actually see a lot of areas where these can become very productive soils if they're drained. So bogs and wetlands, as we mentioned earlier in the ecosystems, were very important agricultural areas because we drain them, all that organic matter that has accumulated then becomes available to the plants and very productive for particular types of crops. On the topography, I think I really already said it, is that it's affecting how those minerals are moving. And if they're moving more, then we get more erosion. We get movement of that soil, which then allows it to develop and form into the different horizons. So the steeper the slope, the more, I guess, effective erosion you can have as that water moves soil particles. It does through the soil, but picks it up and moves it. On flat land, though, we still have erosion. It's just more eroded by wind than it is by water. So topography is very important, but you end up getting usually deeper soil profiles in more flat land. And of course, flat land is desirable for agricultural production because it's easier to plow and till, but also because it's got a deeper soil profile. Altitude, of course, has an effect as well on what type of vegetation can grow there. So in this case, we're looking at like the Rocky Mountains here, where we have a tree line. Above tree line, there's no vegetation, or well, little vegetation. There's still plants up there in some cases, but because of that, there's not as much soil. That rock hasn't been able to break down and interact with the organic matter. We tend to have more soil where we have plant life. So topography can affect that as well in terms of the altitude, which has kind of a modulating effect on that. microclimate. That last factor, of course, is time, and looking at how long it takes for that parent material with all these other interacting factors to be broken down. So, some stuff like granite, a really hard rock, metamorphic rock, can require millions of years for it to become actual soil from that parent material. Whereas something like limestone, which is soft, breaks down relatively quickly. So we develop these soils into the horizons, and if they don't have well-developed horizons, then we consider them young soil, even though really that parent material is probably very old. It's just it hasn't broke down as much and gone through the different weathering. So it's not just time, it's all those other factors interacting too. A mature soil has a well-defined profile and well-defined horizons. So looking at those horizons forming slowly over time, we've basically got, for the purposes of this class, we'll just say really these three horizons. We've got the master horizons. We've got this surface layer, the topsoil, and it tends to be darker. See in the box here, and that's because it's a lot of the organic matter is accumulating there. This is where the most life is. It's the zone of the greatest biological activity in the soil, because that's where the roots grow. Where the roots are growing, that's also where we have most of the bacteria and fungi breaking down the organic matter. That's what we're mostly concerned with, this A zone, especially when we talk about growing annual crops. Tends to be darker, tends to be better. It's what we till and plow and grow crops in. What we owe our existence to, right? A little bit of topsoil. The B horizon, though, below it is just as important. It's the zone of accumulation. So you get everything that comes out of the A zone, it moves down into the B zone. And the difference, though, is that it's generally a little bit lighter in color, and there's going to be less organic matter present in that B horizon. So B horizon is definitely important. It's going to have some root growth in it, especially with more perennial plants. And of course, when we plow, if the topsoil is not very deep, then we're mixing that B and A horizon often. So we call this subsoil. It's not as important for the growth of annual crops, but is still very important for the growth of perennial crops. And then we've got the C horizon, which is closest to the parent material. And there are other horizons that we could have in there, but the big thing with the C horizon is that it's the most like the parent material. And often it's going to have chunks of rock in it. It's unweathered to slightly weathered parent material. And it's what A and B are formed from. We don't really have much root growth in the C zone except for very deep rooted crops and trees. All right, so real quick, all of these particles break down into soil texture, and that soil texture is just defined as the different percentages of sand, silt, and clay particles. And they're just determined, these different classes of particles, by the size of the particle itself. So we have sand going from 2 millimeters in size, visible to the naked eye, down to 5/100ths of a millimeter. Anything in between that is sand. Anything between 5/100ths of a millimeter and 2,000ths of a millimeter is silt. And then anything below 2,000ths of a millimeter is clay. So they're actually not, isn't determined by the parent material as much of what is sand, silt, or clay. I mean, it is to a certain extent, but it's just determined by the size of the particle themselves. And the USDA created this neat little soil textural triangle that really is how we determine the classes of soil based on that mix of sand, silt, and clay particles. And this different textural classification relates to the soil's properties and how suitable they are for crop production. And we're out of time, so I'll come back to this on Wednesday. But just for now, I'll be thinking of sand, silt, and clay and the different, I guess, properties that they bestow upon a soil. So, anybody have any questions or comments, concerns? All right, well, I guess I should probably stop sharing my screen, huh?
You already did.
I already did that, whoops. So one thing I would ask for you all to do, if you haven't already, is just go on there for that crop project and just sign up for whatever crop you want to grow. I think about half of you have already done that. If you haven't already, though, just get on there and tell us what crop you want to look into for that assignment. I've got an example of it on there for you and a checklist, but I'll be happy to discuss it in more detail if anybody needs that. All right, well, you all have a great day. We'll see you on Wednesday.
Another thing I'll say is if you want to experience the soil layers, start digging a hole.
Yeah.
The first few inches are easy, then it gets harder.
Only way to know soil is to actually dig a hole.
Yep. Anyway, y'all have a good one. See some of you in a little bit. Bye.
Okay.